It has started, yeah? Yeah, I can see the time going, yes. Hello, good evening everybody. This is Abhilash here. Welcome to Byju's. We are having a session right now on a very beautiful chapter, thermodynamics. And not just being beautiful, it is a very important chapter. It is something, if you ask me, is a chapter which has double weightage. Why? Because it's there in physics, it's there in chemistry as well. Although, yeah, from chemistry point of view, we go in a very different direction altogether. There are other things in this chapter, like thermochemistry part, for example, is not something that is there in physics. Physics also, I mean, there are sign convention differences and all. But again, even in physics, it's a very important chapter and there are very beautiful questions that come up. Like many of the very important, concepts where you have to really use your brain to understand what is there in the question, such kind of questions are normally in physics. In chemistry, they are more or less relatively straightforward. But again, because it is chemistry, it would be wrong to say that anything is straightforward. Nothing is straightforward, right? So yeah, as far as what we are doing today is concerned, it's titled most important topics as far as JEE is concerned. So yeah, one of the most important topics from physical chemistry is this. And what exactly are we planning to do? So as far as I am concerned, what was informed is that we can go ahead and do a whole chapter quick revision in 1 hour. Now, thermodynamics being a big chapter, I'm pretty sure that you also understand finishing the whole chapter is not going to happen in 1 hour, right? So we'll do as much as possible. So first of all, so as far as this session is concerned, let me clarify a little bit more as well. You might have noticed there is a session tomorrow as well. And tomorrow is when we will be dealing a lot of questions, right? So if you have come here exclusively for theory, you are at the right place. If you have come here exclusively for questions, for example, you're probably not at the right place. But yes, of course, you can brush up your theory today, probably go back and revise your, that weak points and whatever you think, okay, this probably I need to look at it again. And then we can come back tomorrow and we'll solve problems together. Right? So that is the agenda. So quick hi from everybody is what I'm expecting. Can you tell me that I'm audible, visible, all of these, I'm not stuck and I'm not looking like a robot and all that? Will you please clarify it to me? So yeah, updates about JEE and all, please don't ask. See, if I was God, even then I couldn't predict what is going to happen after January, okay? Because you never know. I mean, we just like once bitten, twice shy is what I am right now, because you don't know what is going on with Corona, right? So there are these different variants. I mean, like at one point in time, JEE was the most feared thing. Right now, Corona is the most feared thing, right? So it just is very irritating. It might be a milder version compared to Delta and all. That's what I've heard. Again, I don't want to spread misconceptions here. So I don't know for sure. I'm not a medical expert here to give you sound advice related to Corona. Thermodynamics, of course, yes, I can give you important information, right? So can you tell me, probably, like, is there something that you specifically want to study from thermodynamics? If that is the case, we can focus on that. And specifically, as I told you, today my aim is to teach you theory. Okay, thank you. Some of you, Anmol and all, have said, yeah, I'm audible and visible and all. Really good to hear that. So yeah, if I could get a grasp of, is there something specific from thermodynamics that you want to study right now, something that you find really tough? There are many parts within thermodynamics that some people don't entirely love or entirely understand, but still they are like, okay, let it be, I'm not going to touch this topic. If something comes from here, God will save me, or I'll do 1, 2, A, B, C, D. Okay, I'm going to try my luck today. So I don't want you to do that. So if you have a specific thing that you want me to discuss, I can do that. Otherwise, what I'm going to do is, right now I think there is this delay also, right? So once the chat comes through and all to me, by that time probably I would have already spent a lot of time. Yeah, so I'm seeing a Vishal's message here which says work done via graphs, and there is a monkey face, I think, that he has put there. There is a second law, there is a previous year's questions. As far as advanced questions are concerned, we can take this up tomorrow. I'll definitely convey this to the team. Thermodynamic laws, says Arnav. Again, I think below that, I think there was somebody. Hess's law of constant heat summation. A lot of what is the difference in physics? Okay, one thing, Sonu, try avoiding sending a lot of same chats because then it gets too crowded. I have a screen where I can see all the chat. Just send once. I'll try and scroll. My team here will try and help me scroll through and see what is the yeah, so what is the difference between chemistry? I see Nishant Kumar Gupta's question here. I spoke about this in the beginning. Physics and chemistry, thermodynamics, there is one fundamental difference in, see, chemistry is a very good, nice subject, okay? Not because I am a chemistry teacher. Chemistry is a nice subject. Chemistry is concerned about what is happening to a system. So work done on a system increases energy, there we take it as positive. Physics, on the other hand, is like, okay, let me extract things from the system, right? So physics is looking at everything like a machine in thermodynamics. Okay, if there is expansion, system expands, system does some work for you, that is taken as positive in physics. But other way around, in chemistry, when the system does work, it is taken as negative because it is reducing the energy of the system, and we in chemistry are concerned about the system, right? So sign convention wise, that plus minus difference is there in work done. So that difference you can see even in first law, right? So in chemistry, you have delta U equal to Q plus W. Either you put some heat or you do some work. That is the way you can change internal energy of the system. So delta U is Q plus W in chemistry. Other way around, as far as physics is concerned, what they think is, okay, think of everything as an engine. I am giving some heat. What will that system do? Either it will do work for me or it will increase its own internal energy. So there you can say Q will be equal to W plus delta U. Right? So there is one, that sign difference is there in work done. Other than that, everything is the same, right? So yeah, heat given to the system is positive even there. In physics also it is positive, in chemistry is also positive. That all we'll see as we go. Yeah, so I'm seeing some messages here from a lot of people which is saying, let's try to cover from the basics and go to the advanced level. I really wish that I had that kind of time to start from basics and go all the way to advanced. I'll start from basics because otherwise it will be unfair to a lot of people who are not very probably strong with the chapter, and that is the reason why they have come here. And I start off with the advanced directly and I'm like, okay, let me do this advanced level question. Then they are going to be dejected. I don't want that. I'll start with simple basics. If you want me to spend some more time on something, just drop a chat here. I'll try and go back to that topic and look at it again. Other than that, I'll go through the simple stuff, basic stuff all the way as much as possible. And as far as tomorrow's session is concerned, make sure that you come here for tomorrow's session because we'll take some simple questions as well. And as some people requested, we'll try and do advanced level questions there, right? Because in an advanced level question, almost everything from basic to advanced level, everything is taken care of. So that is yeah, like for example here, Shamoon Azam is saying bond enthalpy. A lot of questions related to bond enthalpy, bond energy, which we look at in thermochemistry, is not something that is there in physics. That is a very important topic because, as I told you in the beginning, physics has those system, expansion, compression, closed adiabatic system. Inside there is a spring doing work or a electrical work or something, and such kind of questions appear normally in physics these days. In chemistry, more thermochemistry and such kind of things are what are happening, right? So yeah, let's begin the session as Rajiv said. Let's go forward. Yeah, so the simplest stuff, where do we start with in thermodynamics? We speak about what you call as, obviously, laws of thermodynamics is what we are going to touch upon. Zeroth law of thermodynamics, very simple. I'm not going to spend any time on it. In fact, what it says is that when two systems are independently in equilibrium, thermal equilibrium with a third system, then those two systems are also in equilibrium with each other. You can see here, there is the system A and B, which is, okay, I don't think you can see me doing anything to B, so I just crashed the whole thing. Yeah, so A and B are both in equilibrium with your C, then A and B are also in thermal equilibrium. What do you mean by thermal equilibrium? There is no more, temperature difference between the two. So when they have the same temperature, we say they are in thermal equilibrium, right? Simple stuff. Now I'm going to look at a very important part, which is called internal energy, right? A lot of people are very confused about internal energy in general. Can I find total internal energy at any point in time? No, we can't, right? So the total internal There was some technical issue. I hope I'm audible right now. I can't see myself on the screen, so I don't know if it's working right now. So bear with us, guys. Yeah. So thermodynamics, right? So what I was saying was we'll go from the basics. We'll talk about all the basic things in the chapter. So as far as the first thing is concerned, zeroth law, we have already discussed. First law, there are different laws of thermodynamics that we look at. That covers a major part of the chapter, right? Beyond that, you have thermochemistry and all. But yeah, a major part of the chapter is your basic laws of thermodynamics, right? So zeroth law, right, say is like almost useless for us, but it just says that okay, if two systems are in equilibrium with the third one, then the two systems are in equilibrium with each other as well. First law relates what you call as your delta U, Q and W, right? So delta U is internal energy change in internal energy of a system. Q is the heat associated with the process, and W is the work associated with the process, right? So this internal energy, what is internal energy? As the name itself suggests, it's the sum total of all kind of energies in a system, right? So there are like kinetic energy. So you can see here translational kinetic energy, which is like movement related kinetic energy. Rotational kinetic energy, if something is rotating, right? So particles can have kinetic energies in rotation, they can have translation, they can have vibration. I can't make this pen vibrate because it will break, right? Other way around, imagine two, let's say a diatomic hydrogen molecule is there. So if I give it energy, it can have this movement where it shows that energy, or rotation, or even vibration. Normally, we don't consider the vibrational energies because under normal temperature conditions where we have these questions in thermodynamics, there that vibrational energy is not going to come into picture. You can imagine if there is vibration, if we have taken the system to that temperatures, high temperatures, where there is a possibility of vibration, which means that the molecule can now break. Molecule can break as in the bond can break and it can separate into atoms, right? So that vibrational energies are not something that we take into consideration in many calculations, but yeah, this is also there, right? Other than that, other electronic interaction energies are there. We speak about these potential energies and all in, let's say for example, chemical bonding, right? So we speak about why are atoms bonded to each other, all of these potential energies. Nuclear energies are also there. There are many other energies as well, right? So there are many energies that we don't even know so far. So of course, it is not possible to find the U total for any system. We don't try to even do that. What we do is, if a system goes from one state, let's say S1 to another state S2, at state S1 it has an internal energy U1, and at state S2 it has an internal energy U2. I can find U2 minus U1, which is basically my delta U, change in internal energy, right? So change in internal energy, heat and work are going to be connected through first law of thermodynamics, which says delta U equal to Q plus W. We'll reach there soon, right? So sum of all of these is internal energy. We can't find internal energy, but yeah, we can find delta U, which for a process or whatever is happening can be positive, can be negative, can be zero as well. If there is no change in internal energy, that is possible. Increase is possible, decrease is possible, everything is possible, right? So yeah, as far as energy, of course, we know energy can't be created or destroyed, right? So law of conservation of energy, first law is kind of parallel to that, right? So first law says that energy has to appear or disappear at some place, but yeah, that is overall conserved, right? So as far as changing the internal energy of a system is concerned, we are trying to move towards first law. You might have understood that. So if I want to change the internal energy of a system, there are two ways to do it. Either I can use heat. What is heat? Heat is energy that flows by virtue of temperature difference. So that is one part, and the other is your work done. Every other kind of energy transaction between system and surrounding other than your heat is what you call as work done. So it can be electrical work or magnetic work, whatever it is. Anything that is not heat is what you call as work. And specifically many times, as far as our syllabus, our questions and all are concerned, this is normally PV work, not compulsorily. PV work means expansion compression kind of work, right? So yeah, delta U equal to Q plus W is basically the fallout of law of conservation of energy. First law is basically a parallel to law of conservation of energy, right? So there are two ways to change internal energy. What is internal energy? All kind of energies. Can I find total internal energy? No. Can I find change in internal energy? Yes. How? Just add heat and work done. What is heat? Heat is energy flow by virtue of temperature difference, hot body to cold body, and as far as work done is concerned, any other energy transfer between system and surrounding which is not heat. Remember that, right? So as far as delta U is concerned, or du rather, so many people ask me what is the difference between delta U and du. So delta U is a significant change, right? From, I mean, it could be zero also, but point is from let's say beginning of a process to end of a process, if I look at the change overall, that is what you call as delta U. It could be a significantly large number, it could be a very small number, it could be anything. Du on the other hand is a differential element, right? Obviously you have studied your calculus, so you know what it means, right? A very small change in U, a momentary change in U. In the middle of a process, at an instant, the change that is happening is du. Du is dq plus dw, where dq is that small change in heat and dw is that small change, a small amount of work done in that instant, right? So it's an instantaneous kind of thing. As far as dw is concerned, work done, as I was telling you, mostly we deal with what you call as expansion compression work, right? PV work is what it is normally called as. So as far as the small amount of work done is concerned, we say that it is equal to minus P external dV, right? So why minus P external? This is also something a lot of people keep asking me about. So I'm going to briefly explain it through a very easy to understand example. I hope you are understanding everything so far. I can't see the chats appearing here on the screen. I'm just seeing the time, so I don't know if you are sending me doubts and all. Okay. So yeah, point is dW I was saying is minus P external dV. Why minus P external? Think about this. Okay, I'm here. Let's say that I'm this person who is a goon and I'm supposed to like punch people and stuff, right? And I'm a bad guy, very bad guy, right? So there are these two people that I have to go and punch, right? I have some strength, right? Whatever, I'm not doing any gym or anything, but yeah, let's say I do gym and I'm like, I have some strength and I'm going to punch two people. There is this one guy who is like already very weak and all, right? And there is this another guy who is my gym instructor, let's say, and he is even bigger than me, right? Let's say, right? So if I look at my work done, right? Is it dependent on me? No. The amount of work done will depend upon what opposition I face, right? So that there's this weak guy I can easily overcome. So the amount of work done will be relatively lower. And if I'm going to tackle the giant, the huge guy, obviously wahan pe I'll have to do more work, right? So work done by me is not dependent on my pressure or my force or my strength. It is dependent on what is the opposition I'm facing, right? I hope this is clear. So that is the reason why we say small amount of work done in a process happening in a system is equal to minus P external dV, the external pressure that is faced by the system, right? So that is minus P external into dV will give me the differential small amount of work done. If I integrate this, if I do a continuous summation of all of these small amounts of work done in a process, I can get the total work done. So we say that W is integral dW, which means integral of minus P external dV. Now this P external, depending upon the process that is going on, the question that is given could be just about anything. It could be constant, it could be varying and all. We can substitute and get a value, right? We'll see. As we go forward, we'll look at some isothermal, adiabatic, isochoric and all of these processes. We'll see, right? So yeah, sign convention, very important. As I told you, physics, chemistry, this is the only difference. This is the only difference in fact, right? So in physics and chemistry, rest everything else is the same. Heat released by the system will be taken as negative, right? Okay, so somebody said repeat, but I don't really know where, what exactly was expected to be repeated. So I'm just going to quickly speak about that work done slide again. So yeah, what I said is that small amount of work done, that differential dW is minus P external into dV, the small dV change in volume that has happened. So minus P external dV is dW. Integral of dW, the continuous summation of dW is going to give me the total work done, and total work done is minus P external dV integral integration. What is P external? That depends on the question. We will see, or that will depend upon the process. We will see as we go forward. More examples we will see. Right. Anyways, in our session tomorrow, we will be seeing questions where this will become amply clear, but I'm just trying to explain nonetheless. Right. So yeah, heat released by system, we put a negative sign to it. Let's say I have heat as given to me as plus 20 joule. What I mean is that heat is given to the system. It is plus, which means that heat is absorbed by the system. And if somebody says W is minus 45 joule, what this means is system has done 45 joule work. See, work done is negative when work is done by the system, right? So they will tell you work is minus 45 joule. It is up to you to interpret that, yeah, this is work done by the system, because I am seeing a negative sign here. They can trick you. They can trick you and tell you work done by the system is minus 25 joule. If they have specifically added by the system, there you will have to understand, okay, something is wrong. I have to look at the sign convention very clearly. But if just they say work done is minus 45, what it means is that the system did 45 joule. System spent 45 joule of itself, and that is why we are taking W as minus 45. So delta U, the change in internal energy in this process, whatever this was, I don't know what it is, will be equal to plus 20 minus 45, which means minus 25 joule. So overall, the system has decreased its energy by 25 joule. That is what this minus 25 means, right? So think about this. What happened as far as the system is concerned? Q is plus 20. So I gave 20 joule heat to the system. But the system is over enthusiastic. It did 45 joule for me. I gave it only 20 joule of heat. It gave me 45 joule of work done. So what is happening is that system is spending its 25 joule to do work for you or me or whoever, right? So what has happened is that the total internal energy change is minus 25, which means system's energy reduced by 25 joule. It's like saying you got 20 rupees to bring, like, let's say chilies for your mummy, and you went there and you put 25 rupees from your side and you bought 45 rupees chili. I don't know why you want so much chili, but yeah, this is the idea, right? So that is the general idea about sign convention. It should be very clear that plus minus, if you go wrong and you do all the calculation, you do integration and your sign goes wrong and your answer becomes wrong, then you're going to be really sad, okay? So yeah, that's the point. Now what is heat capacity? Heat capacity, right? Heat capacity is as the name itself says, right? What is it? Is the ability to store heat, right? So obviously the definition as such is the amount of heat required to raise the temperature of a system by 1 degree C. The general definition, there are many heat capacities. So lot of students make mistake in this also. Think very, more than think, read very clearly what they are speaking about. If a generic term heat capacity is there, it is for the whole system. If they are saying molar heat capacity, that is for 1 mole of whatever is there in the system. If it is like, let's say specific heat capacity, it is for 1 gram of whatever is there in the system and all. So you have to be very cautious, which is that somebody is saying minus P external is the pressure exerted. Yeah, so P external is the external pressure, minus why we are putting that I'll tell you if, that is a good question. Thank you so much, right? So somebody, I think this is what is being asked, why this minus is there, right? So that minus is because of our sign convention. Think about this. Let's say I have a system. There is, let's say, 2 atmosphere that I'm applying externally on it, right? There is this gas inside, right? And I'm giving some heat from below. Let's say there is this burner that is there out here and it's burning this, giving heat to the system, and let's say it expands against this, right? So when the system is expanding, it is pushing against that external pressure. So it is doing work against that external pressure. So it will spend its energy, no? So what we say is, okay, think about this. Let's say by heating, I gave 24, let me use that same numbers that I was using, right? So let's say 20 joule of heat I have given to the system, but on expanding, the system expanded against this and some dV happened, delta V happened. Let's say some change in volume happened. So work done, let's say the pressure throughout is 2 atmosphere. So I'll say work done is, okay, magnitude, let me speak about this. It will be how much? P external is 2 atmosphere into delta V, right? Delta V is what? Change in volume through the process. As far as delta V is concerned, let's say it was some V, right? Some V1, let's say, is the change in volume that happened. So magnitude of work done will be 2 into that V1, right? Let's say final volume minus the initial volume is V1, then delta V is this V1, let's say. Okay? So P external into delta V is going to give me the magnitude of work done. Why am I stressing on this magnitude? This delta V will be positive in expansion. Final volume will be greater than initial volume. Delta V will be positive. Pressure into delta V will be also positive number. This is also positive, this is also positive, final result is positive. But we want work done to be negative. No, we want it to be negative because it is energy that is spent by the system, right? It is pushing against the external pressure. So it is spending its energy to do this expansion. So we want the value to be negative. So what I'll say is, okay, W will be minus 2 into V1, right? So minus P delta V. Of course, this is assuming pressure was constant throughout, which is this 2 atmosphere. Of course, there are other things related to unit and all of that. I'm not going into details right now, but idea is minus is there because of our sign convention. During expansion, P delta V would have been positive. We want work done to be negative during expansion. So we add this negative in front and we make it as minus P external delta dV integration, right? Okay. I hope that is clear. Rahul says why. Okay. Again, because of the lag, I don't know where you are asking the why. I'm really sorry for this, right? So yeah, what is heat capacity? Coming back to it, heat capacity is the ability of a system to store heat. You can think of it like this. Basically, it is how much heat I have to give to increase the temperature of a system by 1 degree C, right? So if I have a very high heat capacity value, what does that mean? I can store a lot of heat, right? I don't want to do that, but yeah, the idea is you might have heard of this, right? When you speak about land breeze and sea breeze and all of these, you might have heard water has a very high heat capacity. We speak of it like this, very common term. Why? Because water stores a lot of heat. It takes time to increase its temperature, right? So something which has very high heat capacity, you will need to give it a lot of heat to increase its temperature. Other way around, if you have something which has low heat capacity, what that means is it has no ability to store heat. Capacity is ability, right? So it doesn't have much heat capacity, which means if you give a little bit of heat also, its temperature will increase a lot, right? So that is the idea. So as far as, let's say that I give a dq amount of heat and the temperature changes by a small amount dt, then I can say dq by dt is the heat capacity. Right? So when I divide dq by dt, what is going to happen is the amount of heat required. Let's say that I gave 100 joule to some system, right? I gave 100 joule to a system and its temperature changed by, let's say, 5 degrees C. It was only 18. Later on it became 23 degrees C. So I gave 100 joule, its temperature increased by 5 degrees C. So I can see logically that if I divide 100 by 5, I'm going to get 20 joule per degree C. What does that mean? For every 1 degree C rise in temperature of this system, I have to give it 20 joule. So when I was starting the process, I did not give any heat. It was at 18. I gave 20 joule, it increased to 19. I gave 20 more, it increased to 20. I gave 20 more, 20 more, 20 more, it became 23. So we can say its heat capacity is 20 joules per degree Celsius or Kelvin, right? Like that, right? So going forward, what we can say is, if I look at the overall process, this is obviously for a small part, differential, instantaneous is what is dq and dt. Other way around, let's say I gave we don't normally write delta q, we normally write q only. So let's say I gave q heat and the temperature changed by delta t. So we say q by delta t is heat capacity. Remember, this is the heat capacity of the system, right? This is one of the heat capacity definitions. Next one is molar heat capacity. What do you mean by molar heat capacity? For 1 mole, how much heat should I give to increase its temperature by 1 degree C is what this is, right? Let's say that same example, 100 joule is what I gave and its temperature went from 18 degrees C to 23 degrees C, and let's say there are 2 moles of substance inside this, right? Then I can say, okay, for those 2 moles, I had to give 100 joule to increase its temperature by 5 degrees C. So if I do Q by N delta T, I'm going to get what is the heat required to change the temperature of 1 mole by 1 degree C. Let's see what is the answer here, right? For example, 100 divided by 5 and 2 are there. Of course, 2 and 5, whatever, right? So this is 10. So what we are getting is 10 joule per degree C per mole. So if I have 1 mole, if I have to increase its temperature by 1 degree C, I need 10 joules, right? So if I have 2 moles to increase its temperature by 1 degree C, I need 20 joules. This is exactly the example that we took before. So in order to increase the temperature of this 2 moles by 5 degrees C, to 20 into 5, 100 joule I'll have to give, and that is the example that we saw. Simple example to understand molar heat capacity, right? So unit and all also should be clear side by side. Now this is a very important topic. I want you all to have very clear attention here. Not something that you will probably get at a lot of places. You don't see it at a lot of places. Let's see. Okay, yeah, swastika, that is the answer, right? So cool. This is okay. Let me ask upfront, how many of you are exactly clear about what is written here? You're very sure? No doubt at all. I'm pretty sure everybody will be sure about this. If you are, just let me know. If you're not, I will tackle this also, but yeah, I'm pretty sure this might be bad for a lot of people. Is this clear to everybody? The genuine doubt, okay? Not too many people might be aware about this because it's normally not taught. I did speak about this a little bit in the beginning where I told you, as far as the internal energy is concerned, we don't take a change in vibrational energies into consideration normally. We take translation and rotation. This is related to that. I'm going to explain this, and for this I need a separate slide, but yeah, I'm going to quickly and make you understand this. If you know this, let me know how many of you here are very clear about this. Leave this you are obviously supposed to know. This column I'm not even asking, everybody should know this, but the second column, if you are very sure about this, this is a very, very beautiful thing to understand. Be very, very careful what is happening here, right? So I'm going to speak about something which is normally not very commonly taught everywhere, so be very cautious, right? So let's say there is a system which has n atoms, right? So let's say H2, for example. In this case, N will be 2, diatomic, right? So the number of atoms is what I'm speaking about here. So let's say, for example, if I have NH3, here N will be 4. I hope it is clear. There are 4 atoms, right, in a molecule. So N is the number of atoms in a molecule. Number of atoms, right? Now, as far as internal energy is concerned, what we say is that delta U is F by 2 NR delta T. How many of you know this? If you know this, say yes, right? If you know this, say yes. F by 2 NR delta T is something that we use. F is number of degrees of freedom. Degrees of freedom, right, of the molecule. N is obviously number of moles, R is your universal gas constant, and delta T is the change in temperature, right? So this comes from, can somebody tell me where is this equation coming from? Can somebody tell me where is this equation coming from? So somebody said iska derivation हमने physics में कर रखा है. This is true, right? So you might have come across this in physics as well. See, this F, this equation as such comes from your Maxwell's law of equipartition of energy. What it says is that there is half RT kinetic energy per mole per degree of freedom, right? What Maxwell's law of equipartition of energy says is there is half RT kinetic energy per molecule per degree of freedom. What a degree of freedom? Specifically your what you call as translational degrees of freedom and rotational degrees of freedom. Half RT kinetic energy per molecule per degree of freedom is there. And when you are considering vibration, right? Vibration, think about this, as I told you in the beginning, hydrogen. There are 2 atoms that are vibrating simultaneously. No, it's not just 1 atom, right? So translation, I can consider 1 atom. Rotation also, I can consider it like, you know, as a molecule, as single unit, right? But as far as vibration is concerned, there is half RT kinetic energy per those 2 atoms. So each vibrational degree has RT kinetic energy, right? Each what you call as translational and rotational degrees of freedom, there is half RT per molecule, and each vibrational degree there is RT per molecule, right? I'll come back to this N. Why did I speak about this N? We'll come to this, right? Now, as far as Maxwell's law of equipartition is concerned, it speaks of half RT kinetic energy. Now, why are we speaking specifically about this kinetic energy? As I was telling you, normally, as far as the initial questions and all are concerned, where we say, okay, there is this diatomic gas and it is taken from this temperature to this temperature in a process and all. When you have such questions, there is no change in delta, internal, and as far as delta U is concerned, we can say it is change in kinetic energy plus change in potential energy, right? So kinetic energy is one component of internal energy. All other potentials, right? All others, right? Electrostatic, magnetic, whatever is there, nuclear, all of these are collectively taken as a part of potential energy there. We can say internal energy change is change in kinetic energy plus change in potential energy, right? Potential energy, a lot of things, right? So we speak of gravitational potential, electrostatic, magnetic, whatever they are, all of these potential energies combined is what is written here and here. Right? Delta K is change in kinetic energy. So as far as change in internal energy is concerned, if I take hydrogen molecule and if I expand it, compress it and all, right? I do a process on it. As long as I'm not breaking it, as long as I'm not breaking the hydrogen molecule into hydrogen atoms, where potential energy can also change, then delta U is only equal to delta K, not delta P. So in chemistry, the processes that we have and all, ammonia is taken from this pressure to this pressure and it is done isochorically and all. If they say there is no change in potential energy, only change in kinetic energy is there, right? So what we say is delta U is equal to delta K as long as there is no change of state or chemical reaction and all going on and all. There we say okay, as long as there is no change of state, there is no bond breakage and all. When I'm expanding, compressing or heating, cooling and all, we say that delta U will be equal to delta Ke, and Ke, as I told you, per degree of freedom, there is half RT kinetic energy per mole. So if there are F degrees of freedom, what is degree of freedom? We'll come back. Okay, how many of you are clear about there is no fixed value? Radhika Mittal is asking, sir, at what temperature we should consider the second column values? Normally we don't consider it. If it is specifically mentioned in the question somewhere or the other that we have a very high temperature system or something like this, where the bonds can begin to break and almost close to that level, if we go there, we'll have to use these values, otherwise we don't, right? So yeah, as I was telling you, kinetic energy per molecule, per degree of freedom. I'm going to explain this degree of freedom thing using a simple atom like helium, right? Monoatomic, right? So let's say I have a helium atom here, right? Monoatomic. As far as kinetic energy is concerned, right? Change in kinetic energy is concerned, it can have translational kinetic energy. You have a single atom. What do you mean by rotation? Anyways, the electrons are going around. Nucleus also has its own internal rotations and all. So rotational kinetic energy is not there in a monoatomic system. If I have a diatomic system like this, hydrogen, I can make it rotate. These are the two possibilities. This is not possible. This doesn't make any sense. I hope you can see it, right? So there are two what you call as rotational axes for a diatomic system. The third one is not there. X, Y, Z we speak of, right? Translation wise, diatomic also has three, just like anybody else. Your helium that I'm looking at, this atom also has translational kinetic energy. X, Y, Z it can go, right? Rotation is not there. Helium, what do you mean by rotate? Anyways, the electrons are revolving, right? And also no vibration. What do you mean by vibration? That single atom vibrating is a part of translation only, right? So there is no translation, vibrational energy, no rotation in a monoatomic, only translational. And every molecule, irrespective of what it is, monoatomic, diatomic, whatever they are, it always has three translational degrees of freedom, right? So every individual atom, if you consider, has 3 degrees of freedom, right? So as far as helium is concerned, it has 3 degrees of freedom, X, Y and Z. And Maxwell said there is half RT kinetic energy per degree of freedom, right? Per mole, of course. If I take 1 mole of helium, there will be half RT per degree of freedom. So I can have half RT in X direction, half RT in Y, half RT in Z. So what we say is, okay, total kinetic energy, right? K total will turn out to be, for helium specifically, it will turn out to be 3/2 RT. So if there are n moles, this is for 1 mole. If I have n moles, then it will become 3/2 RT into N, or you can write it as 3/2 nRT. Okay, mind you, this N is not the N that I started the discussion with. I'm really sorry. I'll come back to that N very soon, right? So here I had a helium atom. which had only 3 degrees of freedom, and half RT per mole per degree of freedom. So half, 3 by 2 RT per mole of helium, and N moles 3 by 2 nRT. So change in kinetic energy, how much will it be? Think about it. Delta KE, change in kinetic energy will be 3 by 2 nR delta T. Right. So in this 3 by 2 nRT, number of moles won't change, right? You have a gas inside a system, it's expanding, compressing and all. Number of moles won't change. You can't make gases disappear. So number of moles is fixed. R is anyways fixed. So if I have to change kinetic energy, I have to change temperature, right? So delta T has to be there, right? So if there is no temperature change, there won't be any kinetic energy change. That is the idea here, right? So delta E, KE is 3 by 2 nR delta T, and this is your delta U as well, right? As I was telling you, there is no change in potential energy that is happening here. So delta U will be equal to delta KE, and delta KE is 3 by 2 nR delta T. This is specifically for helium, right? Now, if I have something else, let's say if I have something like hydrogen, which is diatomic, right? So this formula, we'll come to this, right? So if I have something like hydrogen or oxygen or nitrogen for that matter, right? So if I have two atoms, as I was telling you, even this hydrogen molecule has what you call as 3 translational degrees of freedom, right? So it can go, this is hydrogen molecule, right? And it can go X, Y, Z, that is there. Rotation, as I told you before, this can happen, but this can't happen. This is not using any energy, right? There is no kinetic energy of rotation in this axis. So X-axis, let's say, this, let's say, is X-axis. So this rotation is around X-axis is what we say, right? And this is, let's say, Y-axis. So this is Y-axis rotation. X-axis is there, Y-axis is there, but Z-axis rotation is not there. So as far as a diatomic is concerned, we speak of 2 rotational degrees of freedom. Vibrational degrees of freedom, only one is there. The 2 atoms, right? So one vibrational is also there. If you add these 3, you are getting 6 degrees of freedom, right? Normally, we don't take this into consideration. As I was telling you, under low temperature conditions, I don't expect that vibration will happen, right? So that vibrational energy is not there. It has to be at very high temperature where that also comes into picture. But yeah, normally, we only take these 2 into consideration. Translation plus rotation. Now, one interesting thing is this 6. Why did I speak about this small n in the beginning? I'm coming to that right now, right? So as far as this n is concerned, the point is each atom has 3 degrees of freedom, right? So there are n atoms. Combining all of these, there are 3n degrees of freedom total, right? Including translation, rotation, vibration, everything, there are 3n degrees of freedom. So if I'm looking at hydrogen, where there are 2 atoms per molecule, it has a total of 6 degrees of freedom, out of which 3 is translation, 2 is rotation, and 1 is vibration, which we normally don't consider, right? So as I was telling you, what is this CV? CV is F by 2R. Normally, not always, right? Why do I say normally? Because as I was telling you, there is half RT, right? Half RT per molecule, half RT per mole per degree of freedom for translation and rotation. For vibration, it is not half RT, it is full RT. As I was telling you, there are 2 atoms required for vibration, each of them having half RT each. So a total of RT kinetic energy is there per molecule, right? Per mole of molecules rather, half kT, otherwise we have to take Boltzmann constant, R divided by Na, right? So yeah, point is, normal temperatures F by 2R is what we take. So if I have a monoatomic system, degrees of freedom is 3, that's why I get 3 by 2R. Right? If I have diatomic like hydrogen we just saw, if I consider only translation and rotation, 3 translation, 2 rotation, so 5 by 2R. If I'm considering a triatomic but linear, like let's say something like carbon dioxide, right? Same story, carbon dioxide also has only these 2 rotations. This is not there. This is not going to spend any energy. So we say that, okay, there are 5 degrees of freedom even in a triatomic linear molecule, right? And the non-linear molecule has 6, all 6 of them. Think about this. Let's say I have something like this, right? Sulfur dioxide. It can rotate like this. It can rotate like this. and it can rotate. Now that missing one also can happen right now, right? So all 6 degrees of freedom will be there as far as that is concerned. Basically there are 3 translation, 3 rotation at max, XYZ in both of these, right? So if I have something that is non-linear, I can have Z axis rotation as well, Y axis as well, and X axis as well, right? As we spoke about XYZ, same story, right? So there are 6 degrees of freedom. So 6 by 2 R is basically what is written here as 3R. Now let me go to the second column. Even if we finish second column, no, I'll consider our session to be a grand success, because this is very important. Advanced level है वैसे तो, but थोड़ा सा समझ में आ गया तो बहुत बढ़िया होगा, ठीक है? तो अब क्या होने वाला है? At high temperatures, as I was telling you, monoatomic है, ठीक है? फर्क ही नहीं पड़ता. Vibration is not there, rotation is not there, only translation is there, right? So 3 by 2 RE होगा, तो अभी भी 3 by 2 RE है, right? Remember, as I was telling you, very important that you remember this, that there are 3n total degrees of freedom, and translation and rotation mein there is half R that you have to consider, and vibration mein you have to consider full R. याद रखियो, ठीक है? तो अपने पास monoatomic, obviously it will be 3 by 2 R, because there are 3 degrees of freedom only in a monoatomic. Now in a diatomic, I have totally, as I was telling you, 6 degrees of freedom, right? 3 into n. So diatomic, 6 degrees of freedom. Usme se 3 are translation, 2 are rotation, right? So those 5 of them have half R, right? So 5 into 1 by 2 R is there for the 5 degrees of freedom, translation plus rotation. That last one I was telling you about, vibrational degrees of freedom, there is R per molecule, right? Half R here, half R here. So R per molecule. So plus 1 into R. So what I'm getting is 5 by 2 R plus R, which is equal to 7 by 2 R, which is what is written here. I want you to do the calculation for triatomic linear, right? Tell me about triatomic linear. What is going to happen? Triatomic, 3 atoms, right? So 3 into 3, 9 degrees of freedom are there in all, everything combined, right? Now out of those 9, 3 are translation, 2 are rotation, right? Again, linear triatomic, so only 2 rotational degrees of freedom are there. So we can say out of the 9 total that are there, 3 of them are translation, 2 of them are still rotation. So there are 5 degrees of freedom which are having that half R thing. So I'll say, okay, 5 into R by 2 is from translation plus rotation. Now, out of those 9, 5, as I told you, is here. 4 of them are going to be vibrational degrees of freedom, right? So what are they? That's a different story. Let's say these 2 atoms alone vibrate, or let's say these 2 atoms alone vibrate, middle atom vibrates. 4 degrees of freedom are there in all that we can speak of, both of them vibrate like that, right? So those 4 degrees of freedom, vibrational degrees of freedom, all of them have R each, right? So 5 into R by 2 is 5 R by 2 plus 4 R is there. So you will get 13 by 2 R, which is written here. Specifically, as I was telling you, so I think Captain Jack Sparrow was why vibrations have full R, I told you, right? So for vibration, you want those 2 atoms at least, right? So and this will have that half R and this will have that half R, like that, right? So each vibrational degree of freedom, full R we add. Each translational and rotational degree of freedom we add half R. Sum of all of these will give me the CV values. Of course, this is 13 by 2 R. Here it will become 6 R. Why? You can understand. Because 9 degrees of freedom even here. Triatomic, non-linear molecule, 9 degrees of freedom in all. 3 into 3. 3n is always the total degrees of freedom. Out of those 9, we know 6 of them are translation plus rotation. Here in a non-linear molecule, triatomic molecule, you can have all 3 rotations, as I was telling you, right? So 3 translation, 3 rotation. So remaining vibrational degrees of freedom are only 3, right? So we have 3 which are giving you R each, and 6 giving you half R, right? So 6 into R by 2 plus 3 into R is going to be the total. So 3R plus 3R, 6R is the total. So triatomic non-linear has 6R as your CV at high temperature. 6.5 R is going to be, I think this was asked somewhere. You can understand, this can be asked anywhere, right? I mean, it's easy to make it for a question. Like, let's say ammonia. I tell you, okay, it is not even triatomic. There are 4 atoms. 4 into 3. There will be total of 12 degrees of freedom. Now, out of those 12, you will have 3 translation, 3 rotation. Then you will have 6 degrees of freedom remaining. All of them having 6 vibrational degrees and all of them having R each. So 6R plus the remaining 6 into R by 2, which is 3R. So 3R plus 6R, 9R would have been the value and so on. But again, I'm not going into details. I hope you understood the logic. You can apply it to any molecule you want, right? So this was your CV molar. Understand, this is for molar heat capacity under constant volume. So this is very important. What is that suffix that they have added? What is there below and all? That is important for this, right? Yeah, so then one more table. Let's look at this one more table. I don't have too much time. I really wish we could teach a lot more in 1 hour. But yeah, CP also, you know, what is molar heat capacity under constant pressure? You might be knowing this. CP molar is CV molar plus R. Right, you might have studied this before. How do you get this? Very easy. That's a different story altogether. You can go through delta H angle also, but yeah, this is something that everybody knows. CP minus CV equal to R, right? Be very cautious. It has to be thought of as CP molar minus CV molar, right? It has to be that molar. CP CV in general, if you say, that could mean total heat capacity of system also. So CP minus CV is equal to NR, and CP molar minus CV molar is actually just R. How many of you understood this? Clearly understood this. CP in general, this is what everybody says. Even I said the same thing before I joined IIT, before when I was studying. Even I used to say CP minus CV is R. But be very clear, that has to be thought of as molar heat capacity, right? So as long as you're thinking of molar heat capacity under constant pressure and molar heat capacity under constant volume, CP minus CV is R. Other way around, CP minus CV is actually NR, right? Okay. So yeah, this is very easy now. You know, 3 by 2 R plus R is 5 by 2 R. 5 by 2 R plus R is 7 by 2 R. This is again 5 by 2 R plus R is 7 by 2 R. 3 R plus R is 4 R, right? Whatever value was there in the previous table, how did I reach here? Yeah, so whatever value was there in this table, just add R more to it, you will get CP, right? So CP molar will be 3R by 2 plus R, which is 5R by 2 there. Then 7R by 2 plus R will be what? 9R by 2. 13R by 2 plus R will be how much? 15R by 2. And 6R plus R will be what? 7R, right? So these are the values that are expected here, obviously. 5 by 2R, 9 by 2R, 15 by 2R and 7R. Right? So we couldn't do a lot of things today, I understand that, but yeah, I have 100 slides to teach here. We have reached only 12, but I really don't care. I mean, teaching, again, as some of you said here in the beginning itself, problem solving is going to be more interesting and fun than teaching. And while problem solving, a lot of theory is also clarified by me. I'll teach as I'm in, you know, if I take one single question, when I'm teaching my kids, right, when I'm teaching my students, I normally take up this one question which has all the different possible work done, expansion, compression, all of these, entropy, all of these. I take one question and cover up the entire thermo chapter. At least that, you know, first law based questions and second law based questions and all, I can finish off in one go. Normally that's what I do. I'll try to do something like this in tomorrow's session as well, right? Now, specific heat capacity, as I was telling you, that is for 1 gram, right? So I'm pretty sure you have seen this thing, right? MQ is equal to MS delta T, right? So this S is amount of heat required to change the temperature of 1 gram of gas by 1 degree C. So when I multiply weight into specific heat, that is total weight, how much heat is required to change temperature by 1 degree C. When I multiply it by delta T, it will become total heat required to change the temperature of m grams by delta T, right? So yeah, this is pretty simple. I don't think there is much here. Application of first law is something that I did speak about in the beginning, right? So I was saying delta U equal to Q plus W. Heat given or work done is the only way to change the internal energy of a system, right? Some of the formulas, very important. Delta U is F by 2 NR delta T. Normally, right? In general, you can say delta U can always be said to be NCV molar delta T. Right? Provided CV molar is constant, not something that changes with temperature. Other way around, you can always write delta U is integral of NCV molar dt. Here you'll have to substitute CV molar as a function of temperature if that is there. Other way around, yeah, whatever. That is the idea. Heat under constant pressure, heat under constant volume is delta U. I'm sure everybody knows this, right? Anybody here who doesn't know this? Delta U can be said to be heat under constant volume. Why? Think about this, delta U equal to Q plus W, right? And when volume is fixed, right? Normally when we put this V below, what we mean is that that is a constant. If volume is fixed, work done will be 0. No, we know work done is what? Integral of minus P external dV. If dV itself is 0, there is no change in volume. Isochoric, which means I have a closed vessel in which whatever is happening, right? So there is no change in volume. dV is 0, PdV is 0, P external dV is 0, work done is 0. If this is 0, then Q is delta V, right? The delta U. That is how, in fact, we say, okay, what is QV? Heat under constant volume. What can I speak about heat under constant volume? I can say it is NCV molar delta T. I hope you understand this. This is the definition of CV molar, right? Heat capacity under constant volume, right? Molar heat capacity rather under constant volume. So N into CV into delta T will give me the heat. And that is going to be equal to delta U always, irrespective of process. Why? Because delta U is a state function. We know this, right? So there is this one state S1. From there I am going to state S2. It doesn't matter how I go. It is path independent. Delta U will always be the same, right? So if I am looking at, let's say for example here, let's say there are infinite ways to go from state S1 to S2, but one of those ways, let's say, is where I am keeping volume as a constant, right? Then delta U should be the same even here. So we say delta U will be same irrespective of how I go from state S1 to S2. So if I go from S1 to S2 through a constant volume process, I know that delta U is directly NCV delta T, which means that irrespective of how I am going, what other path I take, doesn't matter. Delta U is always going to be NCV molar delta T. Remember this, right? Or you can remember this more importantly, integral of NCV molar dt, right? Is what you can call as Q. Yeah, this is okay, nice. Yeah, so NCV molar dt integration will give you your delta U. So I couldn't go beyond first law today. A lot of people I've seen here had asked me specifically about the entropy part. I'll make sure that we add questions from entropy tomorrow. First law based questions, again, I'm not very keen to solve them. I told you in the beginning itself, because most of these questions these days in JEE are coming up in physics only, right? Interesting questions are made there. And now as far as entropy is concerned, because it is only there in chemistry, we'll go through that. Other than that, we'll try to look at like somebody, just quickly tell me what all things you need. I want to see all the topics that you want to hear on chat. Tomorrow, specific questions, I'll try and take from there. One is entropy. For sure, I'm going to add a question from entropy change. That too, the gas expansion one or phase change one, that also I'll take. Like, okay, let's say I'm taking a ice at minus 40 degrees C all the way to steam at 200 degrees C. Let's say that kind of, where phase change is also there, gas expansion compression is also there, solids liquids change in temperature is also there. So we speak of delta S as MSL. And okay, I will not give you the formula. We'll solve this tomorrow. That entropy change, that kind of questions also I'll do. Bond enthalpy Shamoun, yes, of course, I'll definitely take a question from thermochemistry which can be solved using bond enthalpy. Do I have space here? Quickly I'll yeah, so okay, the whole thing is going to come up. So let's say if I have something like CH2 double bond CH2 and I add hydrogen to it and I convert it into CH3. Here the delta H, the enthalpy of the reaction, can be looked at in terms of bond enthalpies as well. What we say is that, okay, what is the energy required? I need to first break the double bond, then make a single bond, then add two hydrogens to it. This is what is happening. And then there was this hydrogen bond that I need to break and all. Many of you might already know this, but yeah, we will see one question based on bond enthalpy, so that is also clear. Then what else is there? Gives free energy. Okay, delta G, a lot of questions are not solved here because you know more than thermodynamics, you see delta G a lot in electrochemistry, right? So that free energy aspect is primarily there, but yeah, other than that also G is touched upon. We speak about delta G, because we want delta G to be negative. That second law angle is also there, right? So we speak of delta H minus T, delta S to be negative. That also is there, but yeah, delta G is normally touched upon in electrochemistry. Then thermochemistry, yeah, thermochemistry, Arnav, I'm handling that, as Shamun was saying. One may be based on bond enthalpy and maybe some resonance energy or something. We'll try to see. Other than that, what else is there? Entropy, I'll definitely take up. And let's see this questions. I mean, I'll try to bring up maybe one question from JEE Advanced also, based on the expansion, compression, and all of these as well, right? So I hope all of you will be there tomorrow. It's exactly 1 hour now. I have no idea how we finished 1 hour. It happened so quickly. I didn't even get to drink water. I brought 2 bottles of water. I didn't even drink one. Yeah, so it was nice chatting with some of you guys. I'm really happy that you are active and studying and all. Best of luck. Whatever doubts you have, like keep putting them in these chats and all. Comment, put wherever you want. I mean, you see, as a student, your aim should be that I want to understand things, right? Don't keep your aim as I want to solve problems that happened in last year's JEE, then next year I'll crack. No, understand things, clarify things, fall in love with learning. Automatically, your problem solving skill will increase. But yeah, don't just be, I'm studying, constantly, studying. Apply also. You can't just like learn swimming by looking at YouTube videos, right? So like that, application is also important. You solve questions, you ask your doubts wherever you want, right? Generally, that is also there. But Radhika, the thing is that some of the people here want to end this also fast. Even me, I have to get back home. I have a tiny baby. You might have noticed a small scratch here. I have a baby who scratched me. I just have to go back. He's unwell right now. He's having cough. Plus, some people here have to leave town and all today. Christmas, no, tomorrow. So, Lord, some people are leaving from here and also I wanted to end it exactly at 1 hour. Normally, people stretch it to 1.5 hours. But again, that whatever was to be taught, maybe I could have spoken a little bit more about entropy calculation, MS ln T2 by T1, or maybe like that NCV ln T2 by T1 plus NR ln V2 by V1 that we use in gas and all. We'll try to take, but yeah, let's see. We'll do that in tomorrow's session in problem solving. Theory related to problem also I'll do. It won't be just a problem solving. I won't try to solve 100 questions. I'll try to solve 3-4, but we'll try to cover theory even tomorrow, because 1 hour frankly is very short. Thermodynamics, I normally teach like 15-16 classes, because I try to teach, you know, in a very ab initio method. I try to teach everything slowly and like so that you understand everything. But of course, in YouTube, we don't have that kind of time. You also don't have that kind of time. So we'll try to do things faster. I'll take 3-4 questions where I try to cover all the topics that are there in thermo tomorrow. Same time, Roy. Yeah, 7 p.m. Right, so that is where it is. And I wanted to briefly show something else. Where is that? Where is that link? Wait. Yeah, so very important, free trial classes that we have. The link is there in the description box. Of course, you understand this is the medium for us to communicate to students like you, right? So of course, you know all of these, you know, description, there is the link for free class, you know, like, you know, you can even share it with your friends and all, ask them to come and see. I'm also working on another project within Byju's where we are making the, you know, other than these class kind of things, we have these ready-made, you know, content, very intensive stuff, right? Very beautiful animations and all. I'm working on some of these chapters. Chemical bonding, for example, brilliant we have made, right? So it's so beautiful. Normally chemical bonding, thermo, ionic and all of these are not taught very nicely. Teachers try to don't go into depth and all because it becomes very difficult for student to understand. But we have our product coming out where it's so beautiful, it's so intuitive that you will understand every topic, and we have taught them in a very beautiful sequence. I'm working on all of these. We'll see more of these, right? So that's it for now. We'll see some questions tomorrow. We'll try to touch even advanced level questions tomorrow. Oh my god, who is spamming here? Pi. Sir, how to watch full lecture video? This is not a full lecture video. This is just a live session that we have to interact with students. That's it. Primary aim is to see to it that you guys understand that there are a lot of these. I mean, I'm pretty sure all of you know that there are so many avenues to watch, go through the app and understand, go through some of the videos more. I'm working on bringing out better videos. You will see some of these chapters pop up very soon. Best of luck. See you. Good night. Thanks for coming. Yeah. Take care. Best of luck. Stay safe. No Omicron. Yeah? Take care. Bye.